rest of CPU or the unit running. NP running, Allo running, all other units running.
Yeah, they are running, and other threads can run and do their thing.
No, yeah, so currently everyone doing that.
But you are blocking one
One
thread.
unit.
Yeah,
One unit.
yeah. But that's, that's expensive, right? Yeah. Especially if you're doing it for a long period of time, right? As in you're doing a very large data transfer. If you have a SSD formatted for 16K byte sector sizes, and then you go and do an NVMe command, a single NVMe command could be several hundred blocks in one command, and the CPU, all it does is say, move all this data to these pointers, and tell me when you're done, either because I'm going to pull the completion queue or raise an interrupt.
Yeah, I agree. So moving data to the registers is really a big way.
Yeah,
sure.
Yeah, for sure. It's very fast, so it has benefits. But so they will both exist. Yes. Name and wow, nice to have you.
There's another problem which is even bigger, and that's software.
Mm-hmm.
We know how to write software where persistent memory is block addressable.
Yeah.
And unless you're IBM 34, 36, or 38, you don't know how to write persistent programs with things that are not memory.
Yeah, that's a really good question. It's a great comment, right? So, I mean, as well as investing a lot of time and effort on NVMe, I mean, Andy Rudolph from Intel has been leading a charge on the persistent memory programming model. And this is something that Intel have been doing in collaboration with SNIA. There's some really nice open source stuff on pmem.io. And they are trying to, I agree, we are really in the early, this is why the next few years are going to be so exciting, because as you said, as the gentleman said, we really don't understand what it means to have persistent memory regions in our virtual address space.
The gotcha with that PMEM library, because we're using it, is that there's, it goes to black RAM. I mean, not like it just goes to RAM right now, so it's backed by DRAM, unless you kind of NVM something.
Unless you have an NVM.
But the thing is, there really is no path that offloads it to an NVMe SSD. Yeah.
I submitted a kernel, an RFC kernel patch last week to address that issue. So go check out Linux NVDIM. Yep, it's an RFC. It's up for consideration. We're not trying to get it in the kernel. We're trying to initiate a discussion on that exact topic. How do we take the PMEM driver, which allows me to take a block of RAM or NVDIM and expose it as a block device to the OS that can then be direct access mapped into user space, and extend that to the I/O subsystem through PCIe.
So are you just aggregating writes and then doing it before?
We can take it offline. We're getting really into the. It's a great question. So this has been very good, and we haven't even got to the first slide. But this is the way it should be, right? An open discussion, and there's a lot of bright people in the room. I am certainly not the brightest person in the room, so let's have a good open discussion and enjoy what happens.
Yeah, this is the ultimate
tell that you kind of stacked up.
That's what it needs to be.
Yeah.
You just need to map your entire
Stefan, you should mention about your startup, which you sold to 50.
Well, I did a startup that I sold to PMC.
Well, the startup was focused on.
Well, so my background is actually, I was talking to someone earlier, more way down the physical layer. So I'm an information theory kind of guy. My PhD was in queuing theory, looking at switch over-provisioning, buffering, and the fractal nature of traffic on the internet. Related to a lot of work, really good work that came out of AT&T around the mid-90s. I then got into signal processing, did some work on Ethernet transceivers for wireline, so 1000 base T and 10 gigabit Ethernet. I still have some vested interest in a couple of those companies and whatever. Then got the signal processing techniques kind of merged over to non-volatile memory, so we did some startups around signal processing for the error correction layers in solid-state drives. PMC bought our startup and brought them in, so we helped architect their NVMe controller from the media management side. Over the course of years or whatever, I've got more interested in moving up the stack. So, now I'm much more into, we have a product line of NVMe controllers. We also have a product line of PCIe switches. So I'm very interested in PCIe and how it fits into the compute stack, how I/O memory can relate to system memory, how the kernel treats I/O memory versus system memory, how we can use DMA to move data directly between PCIe devices rather than having to buffer it through system memory, so heterogeneous compute. is very interesting. And more recently, I've also been getting into RDMA. Really good friends with Mellanox. We have John came in the room, who's an awesome Mellanox guy, and we've done a few proof of concepts around how do we take some of this awesome PCIe fast storage, combine it with awesome RDMA networking technologies from companies like Mellanox, and go look at things like block storage with low latency over distance, which is NVM fabrics, but also memory semantic access to persistent memory. So, how do I access maybe a pool of memory that's persistent across an RDMA network with really good latency, and actually maybe have, network attached memory the same way that today we have network attached storage, right? So these, I tend to work way out there, and sometimes my boss is like, "Are you ever going to make us some money?"
Eventually.
Yeah, eventually, exactly. Yeah, exactly. So yeah, so that's the background. So NVM Express and Microsemi, a great team. This is my other great team. Those are my kids. Thank you very much. This is Kiva. She's like 5 weeks now, so I shouldn't really be here. My wife's like, "Are you going to get a good night's sleep tonight?" I'm like, "Yes." Tomorrow night I'll be back home, so my night's sleep will be disrupted again. But anyway, so I'm going to dig into NVMe, and like I said, this talk today we're going to focus on NVM Express. Offline or afterwards, or even during the course of the meeting, we can dig into PNAM and NVDIMs and all those kind of things as well. But I do want to try and make sure everybody leaves knowing a little more about NVM Express than they did coming in. I'm going to give you a brief history of NVM Express, like kind of how we got where we are. Talk a little bit about just how it works, like how do we actually standardize how to talk to a PCIe SSD, which is really the main objective of NVM Express. I'm going to talk about some of the performance aspects. So, like, why do we get good performance? Why do we think that this is a more efficient way of doing things? Why do we think it's better than SCSI? Right? SCSI's been around a long time. It's very good at what it does. Right? So why are we changing things? And then I want to talk about some of the things that we're working on, both within the standards community, within the open source community, and some of the other things that other people are doing to kind of build on this this NVM Express kind of protocol. And like I said, feel free to jump in with comments or questions. If I get something wrong, don't feel free to call me an idiot and just say, "That's not the way it is." So NVM Express actually started officially in 2009. Intel, like I said, Intel has been one of the driving forces behind it. And really, I think, being candid, within their internal development, they realized PCIe was a very important I/O spec for them. They kind of didn't really see a future for SCSI and where they wanted to go. And so they really, to be honest, decided, let's go push a new way of talking to memory, non-volatile memory that's a little bit more appropriate as access times and throughputs go from, maybe if you're lucky, 100 megabytes per second from a hard drive to the easily a gigabyte per second that you can get from an SSD. And seek times that go from 2 milliseconds on a hard drive to 100 microseconds with NAND, and possibly 10 microseconds or less with things like 3D crosspoint and resistive RAM. Right? So this has been a long-term effort. You can say a lot about Intel, and I do say a lot about Intel, but they definitely see the big picture and the long-term plan. Right? This is something they've been doing. Coupled with that, an Intel Xeon today now has 73,000 PCIe lanes coming out of it. It's not quite that many, but you get the idea. They have a lot of PCIe lanes, so they want to hook those up to things. They obviously have their own NVMe products in the SSD space. They will have them in the Optane 3D crosspoint space. Right? So they play in that space for sure. Amber Huffman, who's a fellow now at Intel. Amber just got promoted to fellow like last month, so very well deserved. She's been the editor of the standard and one of the drivers from the Intel side since its start. And she was editor-in-chief of version 1.0. One of the other people who's been there since the very start is Peter Anufric, who's supposed to be here tonight, and I'm his poor second. And he's been driving that, and he still sits on the board of directors for NVMe and is still very active in the standardization. So version 1's actually been around since 2011, so this is not something new. It has taken quite a bit of time to build up, even to the ecosystem we have now. And even that ecosystem, as we were talking about before the meeting started, is still very incomplete. There's still things that are missing from the ecosystem and the infrastructure that we need to go work on. And I'm going to talk about this later. It's very much tuned for performance. It's very much built around, let's not have software in the way of moving the data around. PCIe is inherently coupled to the memory subsystem of the processor. Let's take advantage of that and not have to convert from one data format to another. So an NVMe command at its very simplest is really, for a write command, it's here is a command I'm going to pass to you. Somewhere in that command set is a pointer to somewhere in my memory space. You will DMA this much data starting at that address, right? And you will put it at this specific location on this block device. I mean, that's really what it comes down to. So it's not take the data, flip from big endian to little endian, so divide by 2 and multiply by 6 and add, whatever. It's like take this data buffer and stick it on non-volatile memory, right? And I will get out of the way, right? So once you've initiated an NVMe command, the processor, as we've already discussed earlier, literally does nothing, right? It issues the command. The DMA will happen without the core processor having to even get in the way, right? I mean, that's the beauty of DMA. And then it will get put wherever it needs to go, right? So very much tuned for performance. At the same time, it introduced concepts like multiple hardware queues. Because Intel were also going, well, we can't continue to clock our processors faster and faster because they're going to blow up because they're getting so fucking hot. Sorry, freaking hot. That's like you were talking. Apologies on the other. So they were going, well, coupled with that, also there's inherent parallelism in an SSD, right? We have multiple channels of NAND. It's not a spinning media with a rotating seek head, right? The hard drive only really has one way to access the data. If you have multiple platters, obviously you get more, but typically you have like one thing. So, you can't do multiple operations at once. You've got to kind of do this operation, then move the head to wherever it needs to go, do the next one. In NAND, we have, 4, 8, 16, 32 channels of NAND. And each one of those is capable these days of doing 800 megabytes per second. So that's 32 channels, 800 megabytes per second. I think CNEX had a demonstration of that with Toshiba NAND publicly last week. They were doing multiple channels at 800 mega transfers per channel, 800 megabytes per channel. Right? It's a huge amounts of data. But you can only get all that output if you have parallelism. You can't do one I/O, wait for it to finish, then do the next I/O, right? So you have to have multi-queue, right? So that was a very important thing. So we have support for hardware queues, and I'll talk about that a little bit later. And also they realized that they wanted to standardize at the PCI interface. I like RDMA, but one of the problems with RDMA is they define the standard at the verbs layer, and they let people develop their own drivers for converting from verbs to how you actually talk to the hardware. And the problem with that is the RDMA section of the Linux kernel is a complete freaking mess. Because everybody's like updating their own driver, and they've got this special feature, and like Mellanox love to put in these extra features that are really good, right? But the problem is that it does, it causes a lot of churn in the code base. It makes it very hard for, Christoph Hellwig, who's very well respected in the kernel community, has been trying to tidy that up. And the problem is every merge window, thousands of new stuff patches come in, right? NVMe didn't make that mistake. They didn't try to define the standard at a software intercept level. They went right to the hardware and said, you will have a PCIe bar that is this big, and the registers, the mapping of the registers within this bar is this. If you don't do that, it's not an NVMe drive. It's a proprietary PCIe drive. Right? And there have been PCIe drives around for ages. Fusion.io, awesome company. What Fusion.io did when they did it was truly incredible. Right? They do stuff that today I think is pretty cool, and they did it 10 years ago. Right? Unbelievable. But they were proprietary, and they continue to be proprietary. Right? So they're a PCIe SSD. Yeah. The SSD do a similar thing, but I mean they're doing an appliance, so they can do whatever the hell they like because they don't sell an individual drive. Right? And so what that means is that there's only one NVMe driver, and any work that's done on it benefits every NVMe drive. So every time I submit a patch for an NVMe driver, or CNEX do, or somebody else does, every single NVMe vendor benefits, and every single user space application that uses NVMe block devices benefits too. Right? And there's no There's no vendor-specific stuff. There is vendor-specific stuff you can do, but you can do it through the driver. And so then the operating systems have great support because they only got to do it once. They don't have to worry about Mellanox's driver versus Chelsea's driver versus Intel's OmniPath driver. Just one NVMe driver. And so we end up with very good support in Linux and Microsoft and Solaris and VMware, et cetera, et cetera. And then, of course, we're not standing still. I'm a member of the technical working group, as is Peter, as is Amber, and we are doing a lot of work to extend NVMe. The big one, the one that probably many of you in the room, or some of you in the room are pretty interested in, is NVMe over fabrics. So tying NVMe to a transport protocol to provide distance and scale to NVMe. So think of this as iSCSI for the next decade. Right? So this is going, let's let clients think they're talking to a local NVMe drive, but they're actually talking over a fabric, which could be RDMA or fiber channel or something else, to a server system that's got a huge amount of storage that's basically sharing that out and managing that and maybe putting RAID over the top of it and doing it at access times and throughputs that are unimaginable with iSCSI. Right? So that's kind of where we're going. And then, of course, we're also looking at emerging memories. We've talked about the Intel products. And we're also looking at adding new capabilities to the interface that actually tie into things like log structured file systems and trying to let the host send, for want of a better word, hints down to the drive around locality of data, temporality of data. Is this data around for a long time? Do I expect that we'll be doing lots of read, modify, writes to this file? Allowing the file systems to maybe provide some clues to the firmware that's running on the SSD so that it can do better things around data placement, mainly to reduce write amplification, which extends the life of the drive and provides better quality of service. And then we're also looking at things like providing the drive the ability to go, you know what, for the next hour I'm going to do a lot of I/O on you. I'd like you to defer any background tasks for an hour, and so I get better read QoS. Because the worst thing that happens in NAND is if you get a read from the host blocked by a background write or erase, because if you have to wait for that finish, that read, which should have taken 100 microseconds, now takes 5 milliseconds. Right? Bit of a bummer for your quality of service.
Something like a trim would also be part of that.
Trim, we have that already. It's called the deallocate command. So you can go in and say an LVA range is now erased, and you can take that away for sure. Yeah. Yeah.
I had a question about CPU architecture.
Yeah.
Did CPU architectures have to change to support BIOS coding?
To support.
So would all the CPUs not work with NVMe devices? Is that
so if you have a CPU that doesn't have PCIe, it's not going to work with NVMe, right? If you have a CPU that has a PCIe subsystem and conforms to, at least conforms enough to the standard architecture models to have a Linux variant, it should work with the NVMe drivers. Yeah. So anything that has, for example, Windows support will support NVMe. If it has enough hardware conformality to support NVMe, to have a Windows port, it will definitely support NVMe. Linux should almost always support it. There will be cases where it doesn't, because Linux does run on systems that have no PCIe whatsoever, right? So that's not going to work. But they have pretty good support. I mean, I've like I said earlier, I've done it on PowerPC, ARM64, and Intel in the last week alone. Yeah. And that was a Tegra, by the way, an NVIDIA Tegra Jetson card. That's kind of, ARM, ARM alone doesn't define an architecture because everybody's ARM architecture is different.
Once you go to NVMe over fabrics, you still need a PCIe port?
Yeah, so NVMe over fabrics, I have to be a little careful about it, but what it does is it presents an NVMe device on the client. You don't actually have to have an NVMe device as the backing store on the server. You could use any block-based storage system. So somebody could build an NVMe over fabric server that doesn't have a single NVMe drive. In fact, you could build an NVMe over fabric system that doesn't have a single NVMe SSD in it.
So if you use OmniPath, you don't even need to have block-based, right?
What's that?
If you
Well, so NVMe over fabrics is block-based. If you want to get away from block-based, then you need to come talk to me and John and some of the work that we're doing around memory semantic access to persistent storage. NVMe over fabrics isn't going there yet, but we may go there in the future. So NVMe over fabrics is a block-based protocol.
in other words, it's not defined, it's not specified.
Yeah. I mean, you can take RDMA and memory technologies and create a persistent memory addressable.
So memory pull to memory pull
Yeah.
is not in the spec.
No.
That's what you're saying, right?
We utilize it, but we don't present it to the client, right? There's other technologies, Mellanox and others have that do that already, and we will get more, that will become more popular over time, but NVM Express is today a block protocol and only a block protocol.
And how big is the block?
What's that?
How big is the block?
Well, I mean, so there's two definitions of block, right? There's the drive is formatted for a given block size, so that is one definition of block. But there's also, I can issue an I/O against that block device, and how big is that I/O, right? So at the lowest level, NVMe formatting, the minimum size is 512 bytes. The maximum size is actually 2 to the power of 255, which is more terabytes than will ever exist ever. Right? So you can format the drive for pretty big sizes, and then you issue I/O against that. NVMe allows you to issue I/O that is, I think, again, a very large number of the LDA sizes.
There's a 512 just historical.
512 is historic, yeah. We could do it lower than that. There's been some discussion of that. The problem is the DMA engines are kind of tuned for, typically actually tuned for 4K. I wouldn't format a device for 512 unless I really wanted to,
Yeah, all cache line size.
Yeah, cache line size, now you're really getting to the point where the DMA engine is really not a DMA engine, right?
Now, where's the DMA engine running? Is this on your chip?
Yeah.
Is this the CPU's
It's
DMA
on the
engine?
PCI device. Yeah, So an NVMe device will always have the ability to do direct memory access. Now, it may not have a dedicated DMA engine, as in there's not RTL. They may be using some kind of load store semantic on an embedded processor on the PCI device. But the key thing is the CPU, the Xeon or whatever, is not involved in that memory transfer. Right? Now, in the products that I typically work with, we're in the high performance area, so we have very dedicated, very highly tuned DMA engines that are capable of multiple DMAs at the same time, context, string descriptors, whatever. There is also the option of using Crystal Beach. Right? Crystal Beach is, in an Intel architecture, it's a DMA engine that sits on the PCIe subsystem that's available for use. Now, the problem with Crystal Beach is depending on the BIOS, it doesn't always talk to I/O memory. It's really there. What Crystal Beach was really designed for is if you need to move a large amount of data from this physical address to this physical address, rather than using load store, you could actually initiate an instruction to Crystal Beach, and it would do it for you and tell you when it's done, right? So that's kind of what they designed it for, and they also designed it for talking to network devices, which are PCI devices. But at least on the experiments that we've done, we haven't found great success in utilizing it, to be honest.
No, I mean, if I wanted to build like some crazy TensorFlow hardware that just sort of worked more and more doing things, could we build something where I've got like a layer of RAM, and then when I don't touch it, it'll automatically like flush it out and do DMA without ever having the CPU
Yeah, I mean,
aware of it. So
PCIe devices.
it just looks like I've got this like
A
infinite memory
PC,
space.
from a hardware point of view, a PCI device can initiate a DMA command anytime it likes. If you try to go and do it, if you have a system with an IOMMU in it, part of what the operating system does is it tells the IOMMU what is and is not allowed. Now that's one of the reasons we invented IOMMUs was for exactly that, because there were bad PCI devices that were doing things they were not supposed to do, either in terms of raising interrupts they weren't supposed to be interrupting, or doing DMAs that they weren't allowed to. So one of the jobs of the IOMMU in a virtualized environment is making sure that you can't get rogue guests coming in your hypervised environment and taking over the system by initiating DMAs that they're not supposed to be initiating. So the IOMMU is basically a guardian to the core. And if somebody tries to do a DMA to a region they're not allowed to, the IOMMU will trigger an interrupt, a danger. The OS will capture that and it will actually basically tell you that something bad has happened. Right? And that's supported in many OSs.
Okay.
No, but you could write a driver saying, I know what this thing is doing, and I want it to do these DMAs, and then you're okay because you're a privileged user at that point. Yeah. Sorry, we are really free. Yeah. Next slide. So, I talked about this a little bit earlier. NVMe is very much focused on performance, and like I said, we spend a lot of time making sure the protocol is lightweight. We're moving memory around. We're not translating. We're not changing NVMness. We're focused on pulling as much latency out of the stack as we can. And that means two things. It means latency comes down. It also means that efficiency goes up. I can do more I/O per CPU thread, right? Which means that I have more, either I can do more I/O on my Intel or my ARM or whatever, or I have more spare CPU to go do something else. If I'm in a hyper-converged environment where I'm not just doing storage, I'm also doing compute, right? So with NVMe, these are measurements of SSDs that have comparable performance. So from a hardware point of view, from a PCIe or SATA point of view, these are comparable SSDs. But the main difference between them is the driver stack and anything that's on the path between the processor and the drive. So in the SATA case, right, it's an Intel Xeon for this particular test. I'm going to have to go through DMI to the PCH bridge device, right, because I don't have SATA out of my main Xeon. I got to go to the PCH, and then I go out to a SATA drive from there. So that adds latency, right? That PCH does add latency. On top of that, I'm going through the SCSI driver stack, right, rather than the NVMe one. And what we're seeing is, average latency is roughly half. This is for comparable NAND, by the way. So this is not a NAND variability. This is coming mostly from the drivers and the protocol stack. I'm going from 195 microseconds for a 4K random read at QDEP1 to 93 microseconds. And then my 3.9 percentile, right? So every 1 in 1,000 reads, what's the worst case I see? Here we're nicely tightly bounded to 104 microseconds. Here, the binding is pretty good as well. This is QDEP1. The drive isn't overly busy, right? So we're not hammering it. We're not doing writes and reads at the same time. And then this one, I think, this one for me is equally, if not more so important. Per hardware thread, right? So in Xeon, I get 2 hardware threads per core. With a PowerP open power, I get like 12 hardware threads per core because they have like hyperthreading. I can do 600 megabytes of 4K I/O using one and only one hardware thread. So basically what I did is I just set up FIO saying you're only allowed one thread, go as fast as you can, 4K random, really big file, page cache disabled, you're going to the drive every time. Sorry, not QDEP1, sorry, so this is multiple. This is QDEP big enough and parallelism so I can make sure I'm filling up the pipe. But I am bypassing the page cache. And I get about 600 megabytes per second. SATA, I'm getting more like 80 for one hardware thread. And that's mainly because for every I/O, there's a translation step, there's a SCSI protocol, it's a lot of extra lines of code that has to be run. Yes?
The latency numbers, where are they measured? Are they measured the application FIO?
It's measured at FIO. Yeah.
Context switching into the kernel and
Correct.
going to the kernel stack, with the driver, and
Yep.
transport, coming all the way back.
Yeah, and that includes an MSIX interrupt because I was not polling in this case. Right, so these are interrupt. I have some data on polling I can show you. This measured using a PCIe analyzer, so I can show you exactly what an NVMe. I'm going to get to that.
Just wonder if you could comment a little bit on the comparison between the SAS protocol
Yeah.
and
The SCSI protocol, which is really the official name. Yeah, I mean, so the SCSI protocol involves translation. It's not a case of please just DMA this data to the drive. The processor has to get in the way, look at the data in the buffer, and massage it into the shape that SCSI expects. Right? In the old days with hard drives, that wasn't a big deal because the hard drive is so slow. It didn't matter if you added a few microseconds or even tens of microseconds. NVMe explicitly gets out of that. It says, I don't want to manipulate, I don't even want to touch the data. I'm going to send you a command with a pointer. You DMA that data for the number of cache lines that I provide you, and you put that in the NVMe. I don't even want to be involved. Right? So the CPU doesn't touch that. So
the cost of this, kind of 1.2 1.2 versus a NVMe drive, the cost is considerably higher. Right? Do you see that changing?
I do. Yeah, so someone talked about that earlier. There's really no fundamental reason why a SATA drive should be cheaper or more expensive than an NVMe drive. The media dictates the price of the drive. So there's a few different reasons right now why NVMe drives are more expensive. Some of it is just because the ecosystem is not as mature yet. There just isn't the same number of vendors, the same amount of competition. Another one is that people are still recouping R&D costs, so they're not as willing to drop prices. They don't have the luxury of going, I've already made $2 billion in this market. I can afford to drop my SATA prices because I'm not investing in R&D. NVMe drives tend to be more targeted at the performance market right now, so their SKUs are just inherently higher, right? And they tend to have features that the SATA drives don't have. So we have things like end-to-end data integrity. So we do checks all the way through the data path to make sure we haven't screwed up the data. We may have encryption engines. We may have other features as well, like compression and so forth. So these things are adding up. But I think over time, and I think the next couple of years will be there'll be a pretty big shift in that. And I'm hoping and expecting that NVMe, in terms of dollars per gig, will get much, much closer to SATA and hopefully hit parity sometime in the next couple of years. I work a lot with data center companies, and they're obviously very cost sensitive. And 2 or 3 years ago, I would go into the large West Coast US people, and they'd be talking a little about NVMe, but going, we're going to be SATA for a while yet. The West Coast guys have already transitioned to NVMe. The US data centers are very much in a migration right now. And when I go to China, they're basically a year behind North America. So they've gone, in the time I've been working in this space, China have gone from no way in hell will we use NVMe to we have a committed roadmap. We will be going NVMe, either late this year or next year. Right? So and that's because they're getting pricing data that makes sense for them, and they're getting that information.
No, if you think about it though, like putting flash on SATA is cool.
Yeah.
Right.
Yeah.
I mean, it was like it was never you didn't need to have it go fast. So
Sure. But
this is the obvious next progression.
Yeah. But I mean, the hyperscalers are great at going, it's a kludge, but it's a cost-effective kludge, right? And so the first thing they look at is price.
No, but I mean, historically, this has been repeated multiple
times.
I mean, this is exactly the classic trend.
Don't get me wrong.
Like, almost
I'm hoping NVMe will become pervasive.
Well, I mean, it obviously will. I mean, if you actually look at the history of the evolution of these things, it's quite obvious. It's like, okay, we're just going to want faster and faster pipes into that flash.
It's
now
like
that we've got the capability.
It's kind of like a market crash. It's like, it's going to happen, you just don't know when. And if you knew when it was going to happen, you would make a ton of money. But I think we're getting pretty close. And then just to a point I made earlier, one of the reasons latency is better is because of the software stack, but there's also hardware things that are happening. PCIe devices typically attach directly to the processor, to the PCIe root complex. If you want to, certainly on the Intel processors, if you want to, on the Xeon class, if you want to talk SATA, you have to go over the DMI interface. It says PCIe, but it's really DMI officially, to the host bus, to the PCH chip. Or, this diagram shows us actually connecting to an HBA, right? So I can go talk to a bunch of SATA drives. Right? So that definitely adds some latency. Yeah.
What component of the latency is because reduction is because of the PCH process?
I don't think the PCH is a huge contributor. I don't have data on how long it takes for an I/O to traverse the PCH. But there's going to be a small number of microseconds there, because you are doing a PCH to SATA translation. There's going to be logic gates in the way, things that So it's going to take some time. I don't think it's a huge contributor to this. I think most of it's the software stack, but to be honest, I don't have the measurements. Intel, if they wanted to tell you, could probably tell you. So I've already mentioned this, but because it is a well-defined standard, and I'll talk a little about exactly what that means in a little bit. It has really good OS support. So I work very actively in the Linux kernel. It's open and whatever. We obviously work closely with other operating systems, but those tend to be more behind closed doors. So I can't really talk about that. And yes.
So, having been working with Linux kernel, why don't you hit it like I do? because look, everything in Linux kernel is file based, and if we're going to the world where everything's going to be persistent memory based, the Linux kernel is the wrong kernel.
Are you writing
It's the object based, but that's another story.
I mean, you can MAP stuff, right? I think that's a
but
really
if
good
you
way
do
of doing it.
When you can do memmap, but if you do an up call from the kernel to the user node, the latency on that is horrendous.
But if you do an MAP, there's no context.
No,
right?
But you still have to do it, if you have to like, do like a handler,
Yeah.
or any kind of handler, right? And so the handler is, you write it in the kernel mode, or you want it, and then you do an up call into the user mode, it's a user mode code. That up call is enormous latency.
Yeah.
MMAP's
But
fast, but the
Yeah,
up call.
I think NMAP is going to be one of the mechanisms we do to do that, right? Because you can take, again, we're digressing a little bit, but it's a good digression. PMEM, right, is a driver that allows you to take an NVDIM and expose it as a block device. You can, using Matt Wilcox's DAX path set, I can put ext4 on that, but direct access it. If I mmap a file there, I'm actually changing physical memory on NVDIM by doing load stores on the mmap region that I've now exposed to my user space in my process.
Let's just take it one step further. Now you want to run a piece of code and stream it over that, right? You move the data, and now you want to run a piece of code over it, right?
Yep.
And so what that means is you have to write a kernel mode device driver that's just a simple
No,
upload to user mode.
PMEM, you're already in user space.
This is to do with an algorithm.
I suggest we take it off. Yeah. But I think you're right. It's a really interesting area, and I think PMEM and that there's a lot of work to be done there for sure. But let's take that offline. I would be here all night. So these are some Git statistics I got from Linus's tree last week. I was prepping a slide for the open power talk in 2 weeks, and I thought I'd reuse that slide. So I basically went and I used some Git commands to kind of work out how many times have we changed the NVMe related files in Linus's tree. So this is not an indication of all the changes, because some of the changes get hidden from Linus's tree, obviously. But you can see, these are the commits over time. This is the number of months since January 2011 when the commit started. So you can see a whole ton of changes at the start as the new code came in, and we got a function driver, pretty reasonable ramp. And then, like recently, we've really been ramping up. There's been a lot of work done. I'm going to talk a little about some of the more recent work that's been going on, but there's a lot of work going into the kernel. And then, like I said, when Fabrics goes public and we push what's currently a private Linux patch set public to enable NVMe over Fabrics, we're going to see a pretty big jump for that particular month, and then it will kind of go. And first commit was done by Matt Wilcox from Intel, and there's been 500 commits since January 2009, 59 contributors from over 20 different organizations. So it's got a pretty good kind of momentum. And then the rate of commits is increasing. And like I said, this is not the full picture, because there's merges and things where commits get basically hidden from Linus's tree. But it gives you a rough idea of what's going on. So there's definitely a lot of support there. Obviously, Windows and VMware and Solaris and other OSs also support it. So it has good support. And like I said, we're really working on optimizing that. A couple of more amusing slides before we get into some really technical stuff. So Memblaze is a customer of ours. Memblaze is China-based. They're doing very well in the China data centers. And they build NVMe drives using our SSD controller. So we sell an ASIC controller. and basically it's got embedded processors in it and a whole pile of dedicated hardware for managing NAND. And then they write firmware on top of those processors to kind of differentiate, do their own thing, do some of the some of that kind of stuff. And they've launched a product they call the P-Blaze 4. It's in add-in card form factor, and it's in 2.5-inch form factor. And I was invited to go give a talk at their press launch last year, and that's me in their lab holding up like 2 of the drives, right? So
What happened to your glasses?
what's that? I have contact lenses. So that's very cool. Just to show what a real geek I am, this is my home office last week. This is an NVIDIA Jetson development card. This is the Tegra. So the Tegra is the ARM-based processor. They're pushing that car-based system. It's really good. It's got 64-bit ARM in there. The developer manual for this is public domain, so you can go grab it. It's got like GPU offload engines. It's got DNA. It's got like PCIe. It's like this is a micro server with a huge GPU built into it, right? So I got 7 startup ideas. It's like the things you can do with this, right? But it has PCIe coming out of it, so I can plug in a PCIe card. And so this is an NVMe drive. I can't say whose it is. This is a Teledyne LaCroix. What's that? This is, sorry, Olga. Yeah, I should have put in here. Yeah, whatever. But this is just a little converter to go from a by 4 slot to what's called an SFF 8639 connector for 2.5-inch drive. So that's a 2.5-inch NVMe drive. This guy is running Linux, and I was doing NVMe I/O. I was running FIO. I was getting reasonably good performance. There is actually a problem that's limiting performance. It seems to be related with their IOMMU. So I've actually filed a complaint on the NVIDIA site, and the NVIDIA are now actually going to try and work out what's going on. So they think they'll need a kernel patch to fix an issue to get performance a little better.
Oh.
Yeah, but it's just an example of making sure NVMe works everywhere. This is a picture that I'll be showing at the Open Power Summit in 2 weeks. You guys get it first because you're awesome. This is a Power 8 server. This is an IBM 822SL. So this is the Power 8 processor running Linux. This is running, I think, a 4.0 kernel. So reasonably recent, not fully up to date. And this is a couple of NVMe drives. These are Microsemi drives. These NVMe drives are actually DRAM based. We do a lot of work with all-flash array vendors, and some of them use NVDIMMs for write caching. Others don't like NVDIMMs, so they want a PCIe attached ultra-low latency SSD. They can't buy Intel's Crosspoint or 3D Crosspoint drives today. We give them an SSD with DRAM and then a battery that holds power and flushes the data to a little flash cache in the event of a power loss. Do not buy this if you care about dollars per gig. This is not dollars per gig. But if you care about latency and you don't need a lot of storage, this is awesome. And I use this as a research vehicle to answer questions like, what does the OS have to do if I have an SSD that can do sub 10 microsecond reads?
Did you attach that directly to the memory channel? Because that's one of the things that Open Power.
Well, it's not. This is not an NVDIMM. Yeah, so Open Power also have the memory channel stuff. So it's not just CAPI. They also have the Contudo project, which attaches stuff off their Centaur memory processing thing. But that's not really. I have worked with CAPI, and I do know.
No, this is not CAPI. That's the direct.
I know. Yeah. This is attached over PCIe. This is just an NVMe drive, right? So this is the same NVMe drive that some of our all-flash array customers use in their products with Intel. All I did was took it out of an Intel box, plug it into this box, power up the box. The NVMe driver went, hey, there's an NVMe device on the PCIe channel. I know which binding to do here. It starts talking to the drive. The drive goes, hey, I don't care what processor you are. You're talking to me in PCIe. Everybody knows that language. Oh, you've got a driver that knows which part of me to peek and poke to find out who I am and how many queues I have. Oh, you're issuing I/O against me. Sure, why not? This thing has no idea if it's talking to an ARM, a Power, an Intel, a RISC-V. That's my next objective. Anybody knows RISC-V?
And that power system is running Linux.
Yeah, and that power is running Ubuntu. Yeah.
When's your OS?
Yeah, running Linux. I mean, that's one of the powerful things, right? IBM and the Open Power Initiative are getting to benefit from Intel's kernel development work because they're optimizing the driver. That driver is in Linux. It's in mainline. Open Power works off mainline Linux. They get the same benefit. Intel make the driver 10% faster. NVMe drives in everybody's architecture will get faster. Maybe not 10%, maybe more than 10%, maybe less. There is always some architecture-specific stuff, but most of it is agnostic.
Question about that NVMe card that you have there. You said that it has battery. Like, so what kind of battery is it?
It's a super cap. So it is pretty horrible. Like I said, don't ever use this. I don't think anyone in this room wants to use this device. It's not shown here, but there's a little plug-in. It's like here, and then there's a battery thing. It's a super capacitor. It's about this big, and it hangs off the side. And the idea is that if power is taken away from this card, we'll detect that. There's an early loss power detection circuit on the power line of the PCI channel. When that kicks in, we know we have enough power in the supercapacitor to perform a vaulting to flash. And so on this daughter card, there's basically 16 gigabytes of flash, and on here there's 16 gigabytes of DRAM. So all we do is we know we've got like 7 seconds of power. We basically just read the contents of the DRAM, and we put it in the flash, and we set a little bit in metadata in the flash going, we just had a nasty power loss event. Next time when you boot up, check this bit first. The firmware knows when it boots up, check the metadata table first, find out how we lost power last time. Was it a clean power down, or was it an extreme power loss event? And then basically if it's an extreme power loss event, it goes to the flash vault, it loads it all back in, and away you go.
Is there a process of that or
So underneath this heatsink is our chip that we sell to multiple SSD vendors and hyperscalers who build PCIe SSDs. Inside that chip, there's very high performance DMA engines. There is many, I'm not going to say how many, embedded processors of a certain type that I'm not really allowed to say. We have a DDR interface because we're a high performance SSD, so we do write back caching, which I
can make it easy.
This particular one has a more primitive BCH error correction engine for the NAND, but our more recent ones have low density parity check code engines. We're working with the crappiest NAND that's out there. We're tuned for performance. We have NVMe accelerators, so we're good at NVMe. And that's under that heatsink, right? And that's what we sell. That's typically what we sell. We're not really an SSD manufacturer. We did this because a customer offered us a shit ton of money to do it. And so we did it because they couldn't get it on the open market, and they were willing to pay us a lot of money, and they were a good customer of ours.
Steve, that's not exposed though, right? So if somebody wanted to build a database on your chip and manage that back and forth, that's the big limitation of all NVMs. You can't access that. The controllers. So all it's good for, at least everybody except for Diablo, the only thing they're good for.
Well, remember, this is PCIe.
Yeah, I understand.
Right.
But the same basic idea, though, right? Yeah.
Well, I mean, we present this to the host as an NVMe device.
No, I get that. What I was asking is, can you, programmatically move that between the DRAM and their back and forth?
Or we can use DMAs to do that. Yes.
But only you can do it, right? You wouldn't expose that to a customer. Right?
No, we would. The driver can do that. Okay. Yeah. So you can write something in kernel or user space code that would do that. You could say, I would like you to scrub this range of physical memory that's DRAM attached and make sure that it's in sync with a file that's on a file system on this NVMe device.
So you'd be writing embedded code for your processor.
No, we wouldn't have to touch the firmware that's there. You can do that with NVMe today. Yeah.
So you basically explore memory space.
No, so I think you're talking about, we're still talking, this device exposes an NVMe interface. It doesn't expose a PCIe bar. This device actually does expose a PCIe bar. Yeah. I don't even want to go there tonight because we'll be here for like 14 hours. Yes. Right? So, and yeah, which is awesome, right? Because if you have a DMA master and a DMA slave in the same device, I think that's what you can do all kinds of things. We do actually do that. That's not what NVMe does. We do it as a non-standard thing, right? Yeah. And there's amazing things you can do with that, but we're not going to go there right now. So
I might need another beer.
Yeah. So this is this is a pretty bog standard CPU architecture, right? I got a processor, I got some DRAM attached to it. I probably got some L1s, L2s, L3 caches, right? Those caches are not visible to me in this particular processor architecture, right? They're just caches. I got an operating system. I'm going to use Linux terminology almost always because that's just what I work with a lot. But and inside that OS, there's an in-kernel driver. It's normally a pluggable module, NVMe, right? Some people do user space drivers. There was a gentleman I talked to earlier who's working, an Intel have a user space driver. But this, I'm going to talk about in-kernel driver. And then we have applications on top. Those applications typically use system calls, like read and write, open and close, to talk to the block device. But they can also issue IOPTLs against the NVMe device directly. So there's a couple of different ways of accessing the device. And then down here we have PCIe directly attached to the processor normally, right? We have our chip, which the gentleman just asked about. That chip is basically in the way between the crappy NAND and the awesome storage that you think you have. And I swear, if you knew how bad this stuff was, you wouldn't store shit on it. This stuff is terrible, right? I spent a lot of time managing NAND, and I'm like, I wouldn't store it. I put everything in 7 places. John?
If they need to do PCIe switch, is it ever integrated with the flash controller chip, or are they always separate?
Yeah, that's a good question. So we also do PCIe switches. So there's levels of integration you can do there. Our controller is a dual port capable, so it kind of has a mini switch in the sense that we can either do, we have by 8 in, we can do 2x4s, 2x2s, we can do active, passive. It's almost like a switch, but we also have a real PCIe switch. So it's us and Broadcom are the PCIe switch vendors at Gen 3 speeds. At Gen 2, there's also IDT. You could, in theory, build a PCIe card that had a PCIe switch in the front. Mellanox kind of do some of that stuff with kind of sharing of resources and stuff. It's very, very cool. We can do some of that, but it's not built into this particular ASIC. Most of our customers don't want to do that because typically you're power constrained anyway in an SSD. PCIe 25 watts in most systems, unless you're bringing in external power, like the GPU vendors do. Typically with SSDs, you don't do that. And in 2.5-inch drives, you don't even have an option because there's nowhere to plug in the extra PCIe power connector. 25 watts seems like a lot, but if you're a high-performance million IOP SSD, you can easily get into a situation where power becomes your performance limiter. Not what the silicon's capable of, not what the flash is capable of. It's just the fact that if you ran more IOPS, you would blow up, literally blow up. And we have had cases where we're working with experimental firmware, we're developing new firmware, and we had one case where we literally blew up a server because somebody didn't divide by 8.
Pictures.
Yeah, I know. I really wish I'd got that on video. We had another case where we had a server that had a wonky power supply, and the drive would basically power up, start doing I/O, and it would actually pull the power rail down enough to basically reset the box. So basically, and we were doing boot off the drive, and basically we were stuck in an infinite loop, where basically everything would power up. We would try to basically read and write the drive. The drive would consume too much power, pull down the voltage. The server would detect that, raise a fault, and turn itself off. And we were basically like, okay, not good. So you can do bad things with bad firmware, and it's really easy to write bad firmware. So like I said, NVMe, unlike things like RDMA, they defined the way you talk to the PCIe device, right? So I'm going to show you in a little bit for the Uber geeks exactly what LSPCI reports for an NVMe drive. But basically, we expose a bar. The NVMe standard says, you will expose a bar. That bar will be this big. And you better populate that bar in a way that conforms to the standard, or the driver will not talk to you, and you will not get the NVMe certification stamp. Right? And there's people who do the conformance testing, and you cannot ship a drive with an NVMe logo unless you pass that. Right? So this guy basically knows that this guy is NVMe because when you boot up, it issues a PCIe command that says, I'm a device that has a class code of 7F, and I have a subclass code of whatever, and PCIe SIG has reserved that for NVMe drives. So the operating system goes, I know you're an NVMe drive. I will know the NVMe driver, and the NVMe driver knows how to talk to you. Right? So at that point, basically, it does an I/O remap with Linux. So we basically map it into kernel space, and then we can basically peek and poke at registers just by bit binding on virtual kernel addresses that are mapped within that PCIe bar, right, which is so many kilobytes big. Okay? We don't expose a 7 terabyte region. We don't expose a region that is, I think that's where you want to go, right? We could, physically, can I expose a 7 terabyte bar? If my BIOS supports it, I can, right? Yeah. What I do with that, anyway, there's 7 startups right there. But that's not what NVMe does. It exposes a reasonably small region that we call a mailbox. The driver knows where certain things are within that mailbox, and it will start basically setting up queues and issuing out O commands, and we'll dig into that a little bit. So because they took the decision to standardize here is one of the reasons why it's so architecture independent and so operating system friendly. Okay, so NVMe is actually pretty straightforward. I mean, the standards document's a little scary, like any standard document is when you first read it, right? And the standard documents that are published are public domain. So I have the URL later in the slide deck. Once 1.2 is the standard that's public right now, you can just go get that, right? If you want 1.3, you have to go and sign up for NVMe, and that costs a ton of money. want to do that. But 1.2, 1.2.1, thank you. So there's really three major constructs, and all of these are just PCIe addresses, bus addresses within that exposed bar, right? So it's just a bar, we just map that bar, and the driver knows where everything is within that bar. So some of the locations are doorbells. You write to that, something's going to happen, okay? And the hardware knows that if a TLP comes in for that particular address, it knows something's about to happen. It's going to initiate something, right? So we call those doorbells. We have something called submission queues. Submission queues are basically memory ranges on the host, typically on the host. I'm going to stick with on the host for now. There's some nuances there, but for now they're on the host. These are memory regions that get set up by the kernel. They live in virtual kernel space, but they obviously reside in physical memory, right? And they're going to sit somewhere. Basically what's going to happen is we're going to put blocks of data in this memory region, and it's treated like a queue. And the drive is going to know where these queues live, so it can do PCIe pulls and pull in information from the queue. Right? So the queue is going to basically contain command requests, something I would like you to do. It's a way for the host to tell the drive to do something. And they call those queues submission queues. And then we also have completion queues because we'd like to know when things have completed and be able to understand what has been done by the drive, and so we can take them off. And if we're worried about things like write commits, like if I want to make sure my data is safe, I can't just wait till I've issued a submission because the drive hasn't necessarily processed that yet. So the completion queue gives us a way of understanding when is my data safe? When has the SSD made a guarantee to me that it will look after my data? Right? So we have completion queues. And that's really it. It's really quite simple. The doorbells are known locations defined in the spec. You can go read the spec. There's a certain section that says doorbells are here. Queues are memory locations, but they are mapped to hardware memory, hardware that's in the SSD. Now, an NVMe drive has to have at least one queue, right? And that queue is the admin queue. In theory, you can build an NVMe drive that only has an admin queue, but it isn't going to be very much for you. It's going to basically let you do admin commands, but not data commands. Well, that's not a very good SSD. So most people have more than one queue.
Are they borrowed from PCIe or
they're really borrowed from RDMA in the networking world. So a lot of NVMe stuff, like this concept of submission queues and completion queues, even doorbells, a lot of that is tied into the networking guys. You know, we stand on the shoulders of giants. So yeah.
the doorbells are combination by Bluetooth as well as NVM?
So typically, I mean, yes, there is a completion doorbell, so the drive can actually tell the host. Well, no, that's an interrupt, really. So the doorbell is really so that the host can tell the drive there's something new on the queue. Right? So
it's kind of like
because remember, the queue is in host memory, so if you put something on the queue, all you've done is written to DRAM or your cache, right? You haven't told the drive anything. So the drive doesn't know what to do. And it's not going to sit and pull a memory address all the time because that's a lot of traffic, right? It shouldn't really be there. You could do that. You could set it up so that the driver just makes the SSD always pull the data, but that's not super efficient. Maybe with super low latency devices, we'll start doing that, but that's not typically what we do right now.
You write something to the submission queue and then you can
Yeah, exactly. So you would write a command to the submission queue. Commands in NVMe are 64 bytes. So they're pretty big. They're not huge, but they're 64 bytes. Note that the command does not contain the data. The command is telling the drive what to do, and somewhere in the command there will be at least one pointer that says where is the data with this command, assuming the command requires data. Some commands don't. Some commands are trim or whatever. You don't need to pass a pointer. But for a write or a read command, there will be an address. That address will be a virtual address that will get mapped at some point to a physical address. That address could actually be associated with something that's currently on your swap space. So all kinds of funky shit can happen, right? Because you could issue a command that's on a swap space on a SATA drive that you're going to push an NVMe drive, right? Because you may use a SATA drive as your boot drive because that's more stable, and you don't want to. There's the world of Linux memory management is an awesome world, but yeah.
type of commands can you, if the SSD understands, can you say pause GC now? Can such command be sent?
Awesome question. So today in the standard that's publicly available, there is no way to tell the drive, I would like you to pause background. There is a update to the standard that is currently working through technical due diligence to add exactly that capability. Yeah.
Another question, in addition to I/O, can, if the SSD supports more than I/O, let's say scan or a search or stuff like that, can you do
So,
it's better.
No, I understand. Yeah. So NVMe supports vendor-specific commands. So you can pass in a command. We have something called command groupings, or I think what's the official name? Command categories or something. But basically, the standard commands are a certain category of commands. But then you can basically say, I'm going to have a vendor-specific command domain, and any command that comes in like that, basically all that happens is you pass that I/O down through the block layer to the drive, and that command could be take every piece of data on the drive and invert every bit, right? And tell me when you're done. Yeah. So the capability is there. This concept of using NVMe as a way of communicating between the host and the SSD or device to do more than just storing data, but manipulating data, it's 18 new startups. Yeah, based on my ideas alone, let alone everybody else's, right? Yeah.
So the question completion used is just required from NVMe on a job. So basically it looks like it just requires not just completion. Right?
Yeah.
What about error handling? Were they in the PCIe layer or?
So error handling from a PCIe point of view is handled by the PCIe layer. So NVMe does provide callback functions for things like surprise unplug. So if a drive disappears, we have error handling functions in the kernel that will basically do certain things. Right?
Memory?
What's that?
Error, timeout, memory?
Yeah. So we have, a command completion can return error codes. So you can return an error code saying, I didn't have space on the drive. I tried to do a read, but the error correction capability was too exceeded. So you can return that. There's a whole grouping of error codes.
So this completion is basically the response.
Yeah, absolutely. It's host memory. That what basically happens is, at some point the driver and the host will scrub the completion queue, going, since the last time I checked, what's completed? And what were these status messages? Was this a good completion? Was it an error? If it was an error, what was the error? And it returns that through the block layer back to user space as an error number, basically. So it gets presented to the application. Because remember, NVMe doesn't talk directly. There's no system call that directly calls an NVMe device apart from ioctl. Everything typically goes through read-write, which goes through essentially the block layer and the file system layer. Right? Now we are Jens Exboe from Facebook, who runs the block layer. He is actually adding the ability to provide essentially a private data field with an I/O that would get passed down to the block device. So for NVMe, that means if we wanted to do vendor-specific stuff, we can actually do it on a per I/O basis and start providing tags that say, hey, this I/O, I want you to compress this particular I/O. Or another example is for polling, this is a high priority I/O. So Christoph Helwig has just added a new system call proposal. It's not in the kernel yet. It ties into polling that Jens added recently, and I have some results on that. But the idea is that per I/O, literally per BIO vector, we can assign a priority to it. Yeah. Now, in terms of what the drive does with that, that's a different matter. Right now, the firmware in the drive says no freaking idea what to do with that, but we're getting there. So for the, now we're getting really geeky. I hope everybody can go grab another beer. This is sudo lspci minus VBB on a slot identifier for an NVMe device. This happens to be one of ours before we were acquired. So I worked for PMC Sierra. Microsemi bought us like a couple of months ago. We haven't updated PCIe SIG yet. so well, it takes time. So in the PCIe world, we're still, our PCIe SIG number is still coming up as PMC Sierra until the Linux distros pull in the updated PCIe SIG file. That's okay. I can live with that. And we have a class code So as well as telling PCIe who we are from a vendor ID, we also can identify as a class, right? And NVMe has reserved a specific class code. That's how the driver goes to bind to us as opposed to a graphics card or an FPGA card or a Mellanox NIC or whatever, right? So we can tell the operating system we are NVMe compliant. And there's a whole pile of crap. Don't worry too much about that. This is a PCIe bar, right? Base address register. You're allowed up to 6 of them in PCIe by standard. Region 0 has to be NVMe compliant. Otherwise, you're not an NVMe drive. You're a PCIe SSD, right? I think this size for us is 16K. I think the size will change depending on how many hardware queues you support. So you may not always see 16K there, but there's a definite minimum and there's a maximum and so forth. And it's never going to be super big. Even if you support a lot of queues, you're still not going to be more than, say, 64 bytes, right? Because we're a mailbox. We're not exposing the NAND as memory. In that NVRAM card I showed you, memory regions 1 and 2 and 3 are reserved by the standard, so we can't show them. We have a region 4. That region 4 is 16 gigabytes big. We have 16 gigabytes of DRAM on that card. So as well as talking to us through region 0 as an NVMe device, you can talk to us as a PCIe bar. That's not NVMe, so that's not yet anyway. I'm working on that.
So the mailbox for queue population.
What's that?
Populate queue for the mailbox.
Yeah, so what you're going to do is you're going to have a doorbell for every queue, because you're going to want to be able to individually ring a specific doorbell. And what will happen is in the driver, we look at how many CPU cores we have, and we typically allocate, if a drive has 16 queues and I have 8 cores, I'll basically put 2 of the completion doorbell regions on each core. And I'll basically fan out the MSIX affinity. Right? So this is where I get the parallelism and the NUMA architecture support. And that's something that SCSI didn't have. Right? So we have that ability to scale as people add more threads. I mean, I have a PowerPC box that has 80 threads in it. Right? So, in theory, what's that? It's a Power 8. Yeah. So, and people are doing ARM architectures with crazy numbers of cores, right? And ideally, you'd like to have a completion, a doorbell for each one. Right? So this is just a memory region. The operating system can do an I/O remap. The kernel can I/O remap this. I mean, Linux just supports that, right? I'm taking a physical region of memory and I'm presenting it to virtual kernel space. And then at that point, the driver can just bit bang on that region. And because it knows the offsets of all the registers because they're defined in the standard, I'm communicating with the NVMe drive. Doesn't matter if it's Intel's drive, Samsung's drive, anyone else's drive. Okay? So that's kind of how we get through there. Okay. So, I think we've covered a lot of this, but I'll just run it through very quickly. So let's consider a write command. So someone mentioned the first thing I do is I take 64 bytes of data and I put that somewhere in my memory system. Right? I put it on a queue, the submission queue associated with the core that I'm on. All right, or I could put it on somebody else's queue, but typically I'll put it on the memory address that has been given to me as my CPU bound affinity. Right? So I'm basically pushing it on. That data may just sit on the L1 cache. It may get pushed out to L2. It may go to DRAM. Right? I don't really know. I don't really care. I kind of care if I really care about performance, but that's kind of hidden from me, right? After I've done that, I basically send a doorbell command, which is just basically, I'm going to send you a bang on a given PCIe address. That wakes up the SSD. The SSD goes, whoa, holy crap, what did you just hit me with? That doorbell is associated with that queue. Right? The SSD has been tracking where it is in the queue. Right? It basically has a pointer of the last command it processed, and it knows that the queue is basically a FIFO queue. So it knows that the next element is 64 bytes offset from the last one. So it does a memory read. It does a TLP read. So it basically goes and pulls that address in. Now, the coherency engines and the IOMMU, they all guarantee I'm going to get the data, no matter whether it's in an L1 cache, or an L2 cache, or an L3 cache, or in DRAM, or an L4 cache, or swapped out to disk. It's guaranteed that I'm going to get that 64 bytes of data at some point.
for each doorbell, does the SSD get the entire queue or just 64 bytes?
Well, every time I ring the doorbell, I'm saying there's a new command. Inside the SSD, I'm tracking the address as the SSD sees it. I mean, the address it sees is not a virtual address. I mean, it sees a physical address. It sees the address, and that address could move in physical memory, but the IOMMU will always remap it to where it's supposed to be. And it will actually basically go, every time the doorbell is run, it tracks that. It knows how many commands are backed up. So I can go put 27 commands on the queue and go ring the doorbell 27 times. And over the course of the next whatever milliseconds, the SSD will process those queues. It may pull in all 27 at once if it has enough horsepower to do 27 commands at once. If it's a client SSD, it may only do one at a time. Right? And that's going on for all the hardware queues I support in parallel. Right? So not only can I put a whole ton of queue entries on one queue at the same time, I could have other cores or other threads putting their commands in blocks onto other queues at the same time. Yes?
So you don't know for every, you can't put 5 commands on the queue and hit it once.
What's that?
You can't say.
Yeah, you can do that. So the doorbell isn't just the doorbell. We look at the data in the doorbell, which is actually basically an indicator of where the tail of the queue has moved to. So it is a little more, it's a little simpler than just incrementing by one. So you can put 7,000 entries on the queue. Queues are allowed by stack definition to be up to 64 kilobytes. So 64,000 entries, right? So I could, in theory, put 64,000 commands on the queue and then ring the doorbell saying, I just added 64,000 commands. Come back next Tuesday. And maybe they'll all be done. But, in theory, you can do that, yeah.
Doorbell, does it synchronously process by the NVM card?
Synchronously, as in?
That transfer hits the doorbell.
Yeah.
Is the doorbell available, or does the card get to the doorbell at the point of the doorbell being run? Or?
Yes, because that's a non-cached memory map I/O region. Right, so it knows that it's non-prefetchable. As soon as you ring the doorbell in the operating system, basically it's not allowed to be write combined. It's mapped as non-write combinable. So that TLP to that address will basically work its way through the memory system into the uncore, out through the PCIe subsystem to the specific device. It might take some amount of time as it works its way through, but it will not get stuck in a cache.
And only after all that happens does the doorbell return back.
Well, the doorbell doesn't return. The doorbell tells the SSD there's some new work to be done on the queue, and then the SSD starts doing the work on the queue.
That's asynchronous, right?
It's totally asynchronous at that point. So if you issue the I/O, it really depends on the operating system engine under which you issue it. So if you lose libaio and it's asynchronous, you'll ring the doorbell, and that thread will I/O suspend, right? And it will go to sleep. And if you've asked for an interrupt to be done, basically that thread will not come back to life until the scheduler gets that interrupt and basically brings that thread back into context.
My question was specifically the availability of the doorbell at the NVM card. Does that precede the process going on? Let's say getting context pushed out if it's blocked.
So I believe that the doorbell ring is a posted write, which means it's non-blocking. So the operating system will issue the completion and move immediately on to the next instruction. I'm pretty sure it's a posted write and not a non-posted. Rakesh is nodding his head. He knows more about it than I do.
I don't know more.
Yeah. So I think, we can double check. I mean, that's going to be in the driver code, so you'll be able to go take a look at that. But I'm pretty sure it's a posted operation, and so it's non-blocking. So basically, what happens is now our doorbell's been rung. We know the address of the queue. The doorbell ring actually tells us where the pointer is, so we can go and we know how many. The doorbell ring also contains data that lets us know how many commands have just been added. We basically go and start processing those commands. And like I said, depending on the SSD controller, you may do 1 at a time, you may do 20 at a time, you may do 1,000,000 at a time. That's a hardware implementation specific issue. As you finish the commands, at the point at which the SSD thinks the data deserves to be acknowledged, right, with a write, I can acknowledge the write as soon as I can acknowledge the write before I get the data, right? That's not a very good SSD, right? But I can do it, somebody could issue me an NVM write command saying DMA data in from here and put it in NVM, and I'm like, fuck you, I'm not going to do that. I'm just going to acknowledge the write. You haven't stored the data. You better hope that system doesn't lose power ever, right? Because and also if somebody issues a read to the drive through an no direct access, and you don't have a page cache in the way, you're going to give them garbage, right? You're not going to give them the data that was there. Right? But you could do that. You would be a very naughty person, and you could sell an SSD super cheap because you wouldn't actually need any NAND, but you could do that. Right, so reads, you can't really cheat with reads, right? I mean, we can try and do a read cache in the SSD, but the problem is, I got an 8 terabyte SSD, and my cache is like a meg. What's my hit rate for random reads? It's fuck all. It's not even worth implementing, right? Let the page cache do that. The user wants to, right? Let the operating system. They have a pretty good cache policy, or if somebody's doing a user space driver and they're doing databases, let them cache at the application level. I'm not a big fan of read caching here. Write caching, though, different. If I have an SSD that has like an internal SRAM or some DRAM hanging off it, and if I know I have enough power through a supercap or polycap that I can get that data safe if power is lost, I can do write-back caching. And write-back caching is awesome, right? Pretty much, it's someone here from NetApp, right? EMC, right? Pretty much everything they ever do is about minimizing write commit times, right? So it's like like you basically make a storage company out of solving write commit problems, right? So we do the same here. So if somebody, our controllers are very high performance, so we obviously normally implement write-back caching. And the operating system knows that. We advertise that through volatile write cache settings. Gens has just pushed some new code in for optimizing write-back behavior, right? We're getting better at optimizing for that. So if I tell the operating system I have a write-back cache, he doesn't have to issue a flush instruction to me because I'm basically guaranteeing to him once the data's got to me, I'm safe. So if you do an fsync or a sync up in user space, it'll still come down to the block layer, but now in the new version of the kernel, I don't think it's even in 4.6. I think it's going into 4.6. It's not even in the kernel today. It's being staged for 4.6. Because we're advertising that we'll look after your data for you, the block layer will actually basically just say the sync is done. It won't even pass it down to the drive. Right? And that saves an NVMe command, which is really important to QDEF1. And I'll talk about that in a minute. So we use our DMA engines. We, like I said, client drives may have really bad ones. We have amazing, we can handle hundreds of commands at the same time. We handle ring descriptors. We handle STL. So not only do we pull in contiguous range of data, but you can offer us a scatter gather list, and we can basically combine little bits of data from all over your memory tree and then put it into a single piece of math, right? So, and then on the reads, we can basically read a single LBA from the flash and populate a scatter gather list in memory, right?
Use the word scatter.
Scatter. No. We don't even support scatter gather very well yet. None of the SSDs do. Yeah.
One thing about the read cache we said doesn't make sense because read cache would have the NVMe drive. But why not? I don't understand. You have much larger space inside the NVMe drive than you would have in the DRAM. The page cache.
So I have 2 terabytes of NAND here.
Yeah.
I have maybe a couple of gigabytes of DRAM, and most of that's being used for flash translation metadata.
Okay.
So I can only put like 1 megabyte on read cache.
So you're talking just using the DRAM of the read cache.
Well, what am I going to use? If I use the NAND, I can't use NAND as a cache because that's my medium, right? Yeah.
Same speed then. Okay, well, I mean.
On the SSD. Now, I can use this as a cache to a slower media for sure. I mean, people do that all the time. That's a different thing, right? Yeah. I'm using DRAM on me as a cache to reads coming to me. Yeah.
Okay. Yeah, that makes sense. And the second thing is about acknowledging the app and the block primarily, and this is inside the Linux kernel.
So it's not acknowledging the write, it's acknowledging the flush command. Right. So, the rule is if somebody issues a sync on me, that sync is blocking until all the writes are safe that preceded the sync. Right. Now, if I have a guarantee with the drive that as soon as I have basically got the commands, I'm good, then basically the flush doesn't have to come to me. Right?
So you still have to issue the rights using NVMe, right?
Yeah, absolutely. So the,
Only then can you apply.
yeah, exactly. It's not that big of a deal. I mean, at QDEP1, I've seen some performance improvements with Jens's latest patch. So we definitely act it, but at higher QDEPs, it doesn't really matter as much. It's kind of it's a little finicky thing, but yeah, it's not such a big deal. So our DMA engines are pulling in data for writes, we're pushing out data for reads, and when we complete a given command, we basically update the completion queue associated with that submission queue, and then we optionally issue an MSIX interrupt. Now, we also do things like interrupt coalescing. So rather than raise an interrupt for every single I/O, which would literally, at 1 million IOPS, would literally blow the interrupt handler out of the water. We can basically coalesce I/O. We can look at what's coming and decide, well, I want to acknowledge this I/O because I have another I/O from the same queue. I do things like that. Or the host can turn off interrupts altogether and say, I don't want any interrupts. You're going to be updating the completion queue. Either in a lazy fashion, I'm going to parse it, or I'm going to pull and just have a thread that just beats on the completion queue, which the gentleman was mentioning earlier, right? Yes.
So do you want like single instance of submission and completion queue, or is there like some stream-based model where you can have multiple channels of streams that have the flush semantics?
Yep. Yeah. So I mean, the thread, the queues are independent in the sense that you can basically flush individually on each of those queues. I mean, part of that is because the OS supports that through the block multi-queue work that's been done and been in the kernel since 3.19, and part of it's because of the hardware that's implemented on the drives. Now, some drives, NVMe drives, will only advertise one data queue. They'll have one admin carrier and one data queue, and you're not going to be able to do any NUMA stuff or any of this fancy stuff, right? And they're going to be typically, aimed at client or embedded kind of markets. The enterprise drives will try to have more queues for sure, and those will act as independent entities.
I have fundamental question. Is the SSD always passive or can be active? Can we say?
In NVMe, it's passive, but a PCIe SSD could certainly be active. Now it comes back to the problem: do you really want an I/O device beating on your system memory, waiting for it to change? That becomes a question. But there's technically no reason why a PCIe Fusion AI may have done something like that, right? Yes.
So you had a chart of QDEP1 and you also talked about low QDEP.
Yeah.
But with PCIe and NVMe, how many applications do even use low QDEP, considering the throughput and bandwidth available?
So
is it even practical to talk about QDEP1?
So with NAND, that's a very good point. With NAND, typically you need a queue depth of 32 or even higher to saturate the device because the delay bandwidth product, even for NAND at 100 microseconds, is quite high. 3D crosspoint, the queue depth required to saturate PCIe, 4 lanes of PCIe, drops to about 4. So one of the interesting things about next-gen NVM that people haven't yet appreciated is not only does the latency go down, but the queue depth I need to saturate the device goes way down. And I don't think anybody's really grasped the implications of that, because now I don't need to have long queue depths to get the bandwidth that I want. I can do it at really low queue depths. And that's going to change how things like databases can be done and how we may decide to do parallelism across like key value stores and stuff like that.
The QDEP number determines blocking or non-blocking actually, right?
Yeah.
Because QDEP1 it means one IO. Or
I mean, QDEP does, if you have more than QDEP1 and you're doing blocking operation, it's kind of silly, right?
Yeah.
You're like, right, So I normally.
No, the fact that the QDEP is reducing, but you can saturate the device with lower QDEPs means you could pull instead of block.
Yep. Yeah, for sure. Good to see you, John.
Okay, so
We're going to keep moving.
yeah, well, we can keep moving, or we can just wrap up and have a Q&A session.
Yeah, I'm going to move pretty quick. So we talked earlier, now we're going to get into the real innards. PCIe analyzer. So I'm not even looking at video. I have an NVMe drive. I got a PCIe analyzer. not from your wonderful company, but from
Yeah,
your
I know.
competition.
See?
Yeah, these slides will go online. They'll kind of show you what we're doing, but we were issuing one I/O at a time, so QDepth 1, and this is what we saw. This is for our DRAM-based drive. So the media here is like 3D crosspoint. In fact, it's better than 3D crosspoint. We're using DRAM, right? So like I said, don't buy this drive for dollars per gig.
And don't buy this analyzer.
So, basically, this is telling us what's happening, and these are timestamps telling us how long it's been since the last event. So the I/O command really starts here. This is when I do the submission queue doorbell. So this is when I go, hey SSD, I got something for you on the queue. This is the NVMe SSD pulling in that 64-byte command from the submission queue. So this is a memory read, right? PCI memory read. This is the SSD going, I know where the data is because the command told me I'm going to pull in the data via DMA. And this is a 4K I/O, right? In fact, this is actually a read, so this is pushing data. So this is getting a 4K I/O from the SSD and pushing it to the address that was in the command. So that's it's a PRP, so this is not a scatter gather. This is just pushing contiguous. It may not be contiguous physical address because the IOMMU may put it where it needs to be, but it's not, it's not a true scatter gather. And then here is us, the SSD, updating the completion queue because we're done. And here is us generating that horrible interrupt. Interrupts used to be fast in the world where 10 microseconds was really fast, but MSIX interrupts aren't what they used to be. So this is real measurements for like 100,000 of those I/O done back to back to back to back for that DRAM-based card. So this is like your 3D Octane, right? And this is basically the service time for those I/O measured not at the file system, not at the operating system, not at assembly code. This is measured on the PCIe traces, right? This is as low level as it gets, everybody, right? And this is a histogram of how long those accesses take. There were 4K accesses, and this is measured between the doorbell being run and us issuing the interrupt. So this is not the time taken for the interrupt to have been serviced. This is just the time for us to issue, between us getting the command and finishing the command. Yes.
So can you explain the factor of this variance?
Yeah. So a couple of things here. One is depending on the DRAM address, it may take us longer or faster to get through our memory controller to get to the DRAM, right? Because if the DRAM is doing a refresh, then we basically have to wait until that refresh is finished before we get the data. There's also a little bit of variability because we have embedded processors, and they're doing stuff, right? Even though whatever. And when the command comes in, depending on what line of text code that we're running in our instruction set, it may take us a while to jump to the function that we need to service the I/O, right? And all of those things are kind of random, so we get a beautiful central limit theorem normal distribution. This tells me there's nothing deterministically wrong. And really what's happening is lots of random variables are getting combined together, and I'm getting something that's pretty dicey. You can see that we're hitting an average of around 8 microseconds. We do have a bit of overhead in our controller. So the PCIe is probably like 4 or 5 of this, and we're adding in our SSD another couple of microseconds. But this gives you an idea of like, assuming I have access to memory technology that's really fast, what can I do with an NVMe device?
There is no dependence on the application?
No, because I'm measuring when does the NVMe command start and when do I finish the NVMe command. There's not even any operating system in the way because the operating system is completely out of the loop. This is bare hardware. And this will be architecture dependent. If you have a better PCIe subsystem, this is a Xeon, this is a Broadwell, maybe even an Ivy Bridge. Things will be different on different architectures.
Right. So, what am I missing? Because recently I saw RDMA for convert Ethernet latency of 3 to 5 microseconds.
Additive latency. The additional latency of doing NVMe over fabrics.
So it's not NVMe, it's
No, we need RDMA
Well,
for
so remember, RDMA is doing direct access on the memory. So it's a single PCIe transaction. It's basically going in and doing one of the things. It's doing one of the things in this list of multiple things. One of the problems we have with PCIe is there's a back and forth. I ring a doorbell, right? Something has to go down the thing. That wakes up the SSD. It has to do a DMA. That takes time, right? Once the DMA is done, it puts an entry in the completion queue. Then it raises an interrupt, right? RDMA doesn't do any of those things. It pushes some data to a memory address, and it's done, right? It's one of these things, which is why it's faster, right? NVMe, there's people who are starting to complain that NVMe is too slow.
I mean, if it is RDMA over Ethernet, you still have some processing overhead on the other side. I think this
No, there's
RDMA
no.
over InfiniBand. Okay. There was a Lebanon study where they had like a Lebanon switch in between two nodes, and this was a remote RDMA read.
It didn't even wake up the OS on the other side.
It didn't, but it did.
No, it doesn't.
was on the initiator.
On the initiator side, yes,
And
it
there
does.
was an interrupt for the.
There's no interrupt. There's no interrupt in RDMA. There's no interrupt. It's polling on the queues. Interrupt RDMA polls on queues. So what's happening in RDMA is you have a user space piece of code that basically issues an RDMA read request. The kernel bypasses. It goes directly to the RDMA NIC on the client. It issues an RDMA packet over IB or Rocky or whatever to the far side. That gets converted by the hardware, by the Mellanox hardware. John just left, so we can miss it, into a DMA request that has already been approved when the connection was established. The CPU on this side doesn't even wake up, right? Yeah.
But then the confirmation that the acknowledgement that
No, they are not doing confirmation. If it's an RDMA read or write, there is no confirmation. RDMA read, it's a post and a send that have confirmation, and they take much longer.
numbers are usually just the network latency.
Yeah. I guarantee you that if you did a posted acknowledged command, it would take a lot longer than that. Yeah. So reads and writes are fast because they're not acknowledged. The read is obviously acknowledged inherently because you're getting the data back, right? So you know something happened, but it may not be the data you asked for, but a write, an RDMA write right now is not acknowledged at the client. A send is, but a write is not. Okay? And it doesn't wake up the server on the other side. So right now, there's no way to guarantee an RDMA write actually happened. And that's a problem that we want to try and fix. There's nothing to do with tonight's discussion. But one of the things I'm involved is an initiative to allow for committed writes to occur. But we're going to have to change RDMA for that to happen.
So 10 microseconds is still the best case, right? You have 2 days of one and then no
Yeah.
interference with the data.
Yeah, and remember, some of this is our hardware, so you could have faster hardware that would go a little faster than that. But I think the protocol, probably the best case, is like 5 or 6 microseconds back and forth. And again, it's architecture dependent. We move to PCIe Gen 4, it'll get faster. Right? Not a lot faster, because more bandwidth and delay. If people build better PCIe root complexes, they'll get faster again.
How much? Because I noticed your graph was 0, 0.
Yeah.
How much of that is PCIe latency?
And a lot of this is PCIe back and forth.
No, before the 7.
Yeah.
How much of that? Because your 0 is not a 0, it's 7.
Yeah.
How much of that? The 7.5, 7.3 is roughly the speed of light.
Yeah.
How much of that is PCIe latency that reads going across the wire?
Yeah.
Data across the wire.
Oh, no, for a single PCIe read or write, it's about 800 nanoseconds on this architecture. If I just want to read a PCIe bar address,
No, the 4K data.
Oh, the 4K data. So the 4K of data, yeah, this could be reduced if I did a 512 access. So 4K, it's 4 gigabytes per second roughly. So, that's adding about a microsecond to do the data transfer. So yeah.
So
That's a good point.
Is unlawful.
Yeah. There's a reason why we're all asking for Gen 4 and Intel are saying no. Yeah. So
Can I add one comment? This is DRAM at the back end, so we are able to show the performance of our NVM drive, but any storage flash memory, LPD corresponding or RAM, the controller in the NVM device needs to be now doing paralleling and stuff like that. So this is not going to be, even if the media is faster, real faster.
Very good point. So we have no error correction. Well, we have a little bit of error correction. We have like a Hamming code, right? So super low latency error correction. Even every storage class memory I've looked at will require more complicated error correction. That alone will add probably a microsecond. Like wear leveling, some of that stuff you can get out of the data path, but it's still going to affect things. So you're right. This is one of the things I love about this card. Even though we also make some money off it, is I have learned so much about how we can play around with next gen memories.
Can you buy it?
What's that?
Can you
Sure. I have one in my lab. Unfortunately, we don't sell them like on the open market. You can just buy it from Fry's, but yeah.
We have to rebid on Thursday.
So, yeah, exactly. So, we're looking to the future with NVMe. NVMe over fabrics, we've already talked about it already. We're targeting an additional 10 microseconds or less of latency for NVMe over fabrics. So if it takes you 100 microseconds to do a direct PCIe NVMe access, we want to be less than 110, right? And we're not doing just a single RDMA read or write. This is a storage system. We have to have acknowledgement that the data made it safely. So we have a back and forth, right? We are developing NVMe over fabrics for RDMA and fiber channel. I'll be honest, RDMA is definitely the thing that I'm most excited about. But fiber channel does have its role to play. Like I said, the standard is now done. It's still private. We're basically in a 45-day review period. Should be public by the end of Q2. And there is a group of which I am a member doing the Linux driver work. We're working off a rebased 4.5 kernel. So we are totally up to date with Linus's tree. We have basically a fork of that that's in the password protected area. We have pretty respected kernel developers who are contributing code. And I do know there's some background discussions with the block layer maintainers who will have to approve the patches. So I'm not guaranteed, but I'm confident that we have a path to getting an NVMe over Fabrics driver for Linux in a reasonably short period of time after the standard goes public. We can't push it public today because of some of the NVMe rules around confidentiality and software agreement, blah, blah, blah. But we will be submitting it for review. Obviously, the instant it's submitted for review, it's public domain. You can grab it, you can add it to your own kernel if you want it as a patch set, and you can go play with it. Right? It is working. I'm doing a lot of work with it right now on different platforms. It's very, very exciting. We talked about this a lot. Intel presented some results at IDF. They were showing, interestingly, they were showing latencies not very different from mine. Yeah, interesting. So, 9 microseconds. They'll probably get it better as they get closer to production. This is an NVMe SSD, the Coldstream series. I'm sure if some of you are working for hyperscalers or whatever, I'm sure samples are already out there. I haven't seen any, but I'm sure the big companies who consume a lot of storage are getting their hands on some of those. And that's going to be super exciting. Obviously, the memory channel is also super exciting. That's a different topic. And this will definitely be the first way we will deploy next-gen NVMs in our compute stack. And memory channel needs more work. It's going to take more time. I'm sure it will happen, but it's going to take more time. We're working on things like new form factors and features. So, we have add-in cards. We have 2.5-inch drives that are hot swappable. That's a pretty big deal if you're an all-flash array vendor. You want to be able to pull out dead drives and put in new ones and not have customers. You certainly don't want them to power down their server, and you don't even want to interrupt their services or provide bad quality of service while you rebuild that drive that failed. Right? So we're building standards around how to build these drives and support in the operating system for drives disappearing and reappearing. M.2 is very, very popular in the client space. Apple have been a very large pusher of M.2. They're deploying that in their laptop and iPad series, and they're pushing that. Someone earlier talked about things like streaming or providing hints to the drive. We have a technical working group working on that. So we're looking at that. CNEX, Rakesh is here from CNEX. They've been a big pusher of light NVM, which is not NVMe, but it's the ability to push a lot of the what's normally done in the SSD to the host. It's kind of crazy. It's kind of awesome. I don't know whether the crazy or the awesome will win, but it's kind of fun to play with it and see where it's going. So a lot of interesting things happening. PCIe attached non-volatile memory is definitely going to be a very exciting space over the course of the next few years, as is memory attached, obviously. But I think PCIe will also, they will both have a role to play. There will be competitors, but they'll also be complementary. So it's going to be a lot exciting. NVMe over fabrics, I'm going to start going very, very fast. So you can look at this offline, but basically I got a client, he's got some data. What the driver will do on the client side, by the way, the driver we're developing is for both the client and what we call the target. Right? So the Linux kernel will support both. If you're a client, you'll basically create a connection to a server, and what happens is magically in Linux, a /dev/NVMe0n1 will appear. You're like, well, I haven't bought an NVMe drive. Who's put this here? And you will be able to issue I/O against it. You put a file system on that drive if you want. You'll issue I/O against it, either direct or FIO, whatever you like. It just looks like it's an NVMe. You'll even be able to issue admin commands against that drive, and those admin commands will return successfully. They're like, holy crap, I just got an NVMe drive for free. Bonus. You issue an I/O on that drive, what happens is, like we said earlier, you basically create the command as a 64-byte entry somewhere in memory on your submission queue, and you ring the doorbell. Now, what actually happens is in the kernel, it goes, hey, that /dev, that's not really here. That's somewhere over an RDMA network. I'm going to take that 64-byte command, and I'm going to stick it in an RDMA packet, maybe with some other commands, and I'm going to push it over the network. Ooh, RDMA. Ooh, it's here. What happens is you basically have a receiver for that queue on the target side. It basically takes the command, pops it in the queue, and assuming you're using NVMe drives, it then issues a standard PCIe NVMe command against the drive that's associated with this drive. It doesn't have to be a one-to-one mapping. There's all kinds of funky ways you can carve up N drives here and present them to 1 billion clients. There's all kinds of ways. People are going to. There's 87 startups right there. Right? So lots of ways you can do that.
So when you said it shows up as /dev/NVMe,
yeah.
If I do a disk usage or something, will it show you the collective usage of the whole?
No, it will present to you depending on the criteria, the quality of service criteria that's basically arbitrated between you and the server. So here you might have a 20 terabyte drive. This guy might only see a 1 terabyte drive. There is a layer of indirection in terms of what we expose to the clients and what we actually have here. And that's very standard for storage services. Right? It's all about virtualization, taking a large block of storage and presenting it in different ways to different ends. We can even do things like have different quality of service. So you might pay for 80 IOPS, you might pay for 1 million IOPS. And, this thing is going to, like I said, there's going to be 87 startups, right? Companies like NetApp and EMC and whatever. These are all problems that we solved in SCSI, and now we're going to have to solve it at orders of magnitude higher performance and orders of magnitude lower latency. For here, we're using the RDMA nodes a lot, so we tie into the RDMA nodes. So anything that talks RDMA could be here. So this NIC could be InfiniBand, it could be iWarp, it could be OmniPath, it could be whatever. As long as it's RDMA compliant, it could be 2 squirrels. And as long as you have a squirrel RDMA driver here, it might not be very fast. The squirrels might get crossed, but it could be squirrels. Sorry. All right, very near the end. I think everybody's like, I am anyway. Polling, so we've already talked about this. The drive can send out an interrupt. I'm not going to go through these slides. I'm just going to show some data. The cool thing about polling is your latency comes down. So this is MSIX interrupt based. This is polling based. This is now in the kernel as of 4.5. And Christoph Hellwig and a few others are tying it up to application space through new system calls. So this is in the kernel, but it's not actually accessible to applications yet. And this is SDPK, which is Intel's user space driver, which is basically totally bypassing the kernel. And these are the number of IOPS, which is really just 1 over the average latency, because this is QDEP1. And this is the quality of service metrics of 4 nines on latency. And this is the CPU utilization. So SDPK, a little bit better on average latency. It's certainly better quality of service, but you are forgoing all the wonderful services the kernel gives you, right? So if you really care about performance, low user space, but beware, you aren't going to get all the nice things the kernel gives you because you've bypassed it, right? So, yeah.
Just, sorry, just one last, on this last slide, right?
Yeah.
One of the ththings is the OmniCap is not already invented, right? So that means they're going to go through a software layer, right? Does that mean?
OmniCap is already in it.
They're implemented by
They're in
Well,
InfiniBand.
InfiniBand-like, but I'm just saying is there's a software layer.
Rocky actually has implemented that.
Yeah.
And you can run Rocky.
Yeah, but what I'm asking is, there's a software layer that you have to get, wouldn't that be more inefficient?
It's going to be very comparable to InfiniBand in terms of performance.
It's basically a UDP, IP, and then you have a.
And we may be violating NDAs with Intel by saying that, so I'm not going to say too much more. The downside, of course, is if you're polling, you are banging on a memory space, and you are consuming a hardware thread. So this is CPU as measured by hardware thread. So the downside of polling is I am now basically committing that thread to doing nothing and nothing. You know, in theory, if the CPU was busy enough and the Linux scheduler kicked in, it would actually kick you off. But you can set up your polling priorities, and there's all kinds. There's 7 startups right there. Right? Just getting this stuff implemented, right? So
Yeah,
I know.
Certainly over the ladder, so.
Yeah. Yeah, exactly. So, you know, as per usual, I've run way over length. It's been awesome. You've been a great crowd. So just to finish off, and then I'm literally going to follow. NVM Express standardizes, right? Really important. I think this is really key why it was so successful. It standardized how CPUs communicate with PCIe attached SSDs. It took what was a fragmented market, and you know, by sheer brute force and the fact Intel were really driving it. And, Intel is definitely my frenemy. But they really took a long-term view here and said, we need to standardize this right at the PCIe interface level. We want a single driver. We want that driver to be well supported in the major OSs. And we want everyone in the NVMe community to benefit by the work that's being done in there. So it's not, it's not a case of X benefits and otherwise, everybody's working towards a common goal. I mean, obviously we fight in the marketplace, but everybody benefits when NVM Express drivers get better, right? It's very much focused on performance. We're memory, we're not memory semantic in terms of load store, but we're memory semantic in the sense that we don't convert the data, we don't pass it through a software layer or protocol transaction. The NVMe command is basically take this much data from this physical memory location and stick it on the SSD, right? Don't get in the way. Right? We use DMA, we use NUMA support, so we can have queues on every single processor. And like I said, some people are complaining at the 6 or 7 microseconds. Maybe we got to do some work there. It'll be very interesting to see what happens as things like 3D crosspoint and resistive RAM become more pervasive. We are looking to the future.